Hello, my dear students. Welcome to our SChemEs lecture. Today, we want to discuss together what exactly we're going to have in your FPC Practical Skills Assessment. This skills assessment constitutes 10% of your overall module mark. First, let's start with some general instructions. You need first to arrive in plenty of time before your SChemEs test, at least 10 to 15 minutes before your scheduled time. And any student that will be arriving late for the SChemEs test may not be admitted to the test. Please bring with you a pen, pencil, ruler, calculator, that should be a university approved one, and your student identification card. And make sure not to forget your white lab coats, otherwise you will not be able to attend the exam. Your practical skills assessment is divided into 4 main parts. Actually, in the exam, you would pass by 5 main stations. Station 1, 2, 3, 4, 5. In every station, you would stay around from 7 to 10 minutes as you'll be instructed. And once you hear the word switch, you need to move from the first station to the second station. The ones in station 1 would move to station 2, and the ones in station 2 would move to station 3, and so on. And the last ones that are at station 5 will move to station 1. So you will gonna have your exam paper. It will be the same paper with you, and you will pass by the 5 stations. In every station, you may find something practical that you will do, or you may answer the question that is found in your exam sheet. In this lecture, we will move on the 4 important sections that you will need to focus on while preparing yourself before the SChemEs exam. First, we will start with the basic skills, and then we move on the glassware manipulation and how to use the most important glassware that you have in the lab. Third, the interpretation part, and fourth, the numeracy part. Let's start with the basic lab skills part. In your basic lab skills part, you have 2 major things that you need to make sure that you can do efficiently. First, weighing by difference, and second is the different separation techniques. Either you have a liquid with an insoluble solid inside, or 2 liquids that are immiscible together. How to separate both of them from each other. Let's start first with the weighing by difference. In the weighing by difference, you need to know that this technique, it represents the most accurate measurement way for a quantitative assessment. Okay, if you need to measure a certain mass of a solid sample accurately, that's why please make sure that you need to have your weigh in a 3 decimals. Always get all your weighs in 3 decimals. Take all the number that you will have on your balance. As we discussed before, the best and the most accurate way to weigh is using the weighing by difference technique. That's why you're asked to weigh by difference. How do we do this? First, if you're asked to weigh, for example, 0.3 grams, تمام? What you will do is, first, you need to tare. So the first and the most important step and the most important keyword is to tare. You will need to tare your balance while it's empty like this first in order to get the zeros. After tearing, you're gonna place your boat or whatever thing that you will have as a container, you're gonna place it empty, and you will record and assign its weight, of course, to the 3 decimal places. Okay, I will just record it because I will leave it on the balance and I will check. If it's 12 grams and I will need to add 0.3 grams, then I will keep on adding the powder till I find the reading of the balance reached the 12.3. Okay? طيب, do they need to be accurately 12.3? No. If you got it 12.31, it's okay. If you got it 12.32, it's okay. no problem with this. Why? Because we will then take the boat together with the powder, and then you will remove the powder into the vessel or the other container that you will be provided with. Fine. And now I will have my boat having a dirt inside. Not all the powder you balanced moved into the flask. So you will weigh back your boat, but this time you're gonna weigh it with the dirt inside. تمام? So of course you will get it 12, but this time it would be 12.08 because the most of the 0.3 was already transferred into my flask. طيب, how can I get this weight which is inside the flask? How can I get this measured weight? I will get it by difference. Which two readings that you will subtract? I will subtract the 12.3, which is the boat plus the powder, minus the boat plus the dirt. So the boat plus the powder minus the boat plus the dirt would give you the amount of powder accurately transferred within your conical. So again, please make sure you just weigh the boat because you need to know how much exactly you will gonna add. This is number one. Number two, after you transfer the powder into the flask, you measure it empty. Why? Because I need to subtract the container with the dirt minus the container with the powder I added to get the amount that was exactly added. Yep. And I asked you to weigh 0.3. Now you told me that my accurate weight is 0.22. No problem. It's okay because this is just the accurate measurement. You were desired to weigh 12.3. If you added 12.3, 12.31, 12.32, it's okay. And whatever you get by different, it will also would be okay. It's very important to tear in the first step while you have nothing on your balance, while it's empty, till you get the zeros. And then you have to ensure that you recalled all your weights in your exam sheet. And your exam sheet will be provided with a table like this. First, you get your boat and you write the boat plus your chemical here. Like the one we wrote here, it was 12.3, for example. And don't forget to write it in 3 decimal places. And then you remove out your powder into the beaker or into the conical or whatever you are provided with. So now you have the dirty boat. So it's also the boat plus this time what? The dirt. How can I get the boat plus the dirt? It will be around still 12, but we can have it 0.02, 0.01, whatever. So the third step would be your calculation. You will get the difference between both of these. 12.300 minus 12.020. So I will get my weigh by difference. Also, it has to be to 3 decimal places. Make sure that you fill in the whole table and you write your answers to 3 decimal places to ensure the full mark. In the second part, we said that we were gonna discuss the different separation techniques. So we will either separate a solid which is insoluble from a liquid, or we will separate 2 different liquids. Then how can I separate an insoluble solid from a liquid? Of course, we used to do this by filtration. And what's faster than the regular filtration is the vacuum filtration that we used to do it, and in our labs we used to connect it with the water supply in order to apply low pressure and to help in facilitating the filtration. So make sure that you attach everything perfectly. The Buchner funnel here above this Buchner flask, make sure that you use the correct filtered paper with the optimum size before adding your insoluble solid with the liquid. Because if you didn't add this filtered paper, everything will move down into the Buchner flask and you will lose your precipitated. So to separate the solid precipitated from the liquid, make sure you add the proper filtered paper. When will you use this apparatus? Once you have insoluble solid in a liquid. But what will you do if you have two immiscible liquids? Now I have two immiscible liquids. I cannot do a vacuum filtration, but instead I will do the liquid extraction or the separation method using the separating funnel we used to use. Can you remember? In the separating funnel, you can separate two layers where the lower density layer would be the upper layer and the higher density layer would be the lower layer. We never know which is the organic and which is the aqueous unless we check the densities. The one with the lower density would be the upper layer and the one with the higher density would be the lower layer. So if we have a chlorinated solvent, for example, then they will be the ones with the higher density, so they will be the lower layer. If we have an alcohol and ether, for example, then they will be the one of the lower density, which is less than 1, where 1 is the density of the water or any aqueous media. Okay, so again, we need to separate two layers. One of them is aqueous and one of them is organic. The aqueous always have a density of 1, and the organic, it can be higher than 1 or lower than 1. If it's higher than 1, then it would be the lower layer, and if it's less than 1, then it will be the upper layer. The aqueous layer is the water-soluble molecules in there. Any water-soluble molecule will be found in the aqueous layer. Any ionizable molecule that can form an ions with a plus and negative will also move into the aqueous layer. However, the organic layer would constitute any hydrophobic molecule, any molecule which doesn't love the water, but will rather prefer the organic solvent, or any non-ionizable molecule, any molecule that cannot form ions, that is covalent bonded, will also be found in the organic layer. It's very important to know how to hang your separating funnel. You have to connect it from the neck like this. You have to make sure that this tab is always closed, and once it's closed, it's found horizontally like this to prevent the passage of the liquid. Once you make it vertical, then you opened it and you allow the liquid to move down. So always make sure that your funnel is closed and that your stopper here is in a horizontal position. We used to add the two liquids inside the separating funnel. We hold it like this, as you can see here in the picture, and then you shake, don't forget to vent to release the internal pressure, and then you place it on the stand as it appears here in the image. In our exam, you're not extracting a solid from the liquid, so you will not need to shake so much. You will just need to shake a very little bit in order to separate the two liquids and to leave them to stand. Then you will start collecting the lower layer and the upper layer, where the lower layer is the more dense and the upper layer is the less dense one. And you will never know which one is aqueous and which one is organic unless you're provided with the densities. After we're done with the basic lab skills, now we will move to the glassware manipulation. And in our glassware manipulation, you need to know 3 important parts: how to set up a reflex, how to use the separating funnel, and how to set up a burette and take the initial reading. For the reflex, why do we use the reflex? We use the reflex if we want to keep a certain reaction for a long time under high temperature, and we need to heat this chemical reaction for a long time together with stirring. So in order to prevent the solvent from evaporation and my reaction from burning, then I will need to use a condenser where we apply a water from a lower inlet and then we collect it back from the upper outlet in order to cool the vapors that arise from the reaction. And once those vapors are cooled, they will recondense back into the flask, and then I can keep the solvent amount constant within the reaction. As you can see here, those are the dripping vapors, which was the solvent that evaporated on hot, hitting the cold surface and then condensing back into the reaction, so you kept your reaction constant. When do you use this? If you want to keep the reaction for a long time under a very high temperature, so you want to keep your solvent and you want to keep your reaction constant without any change. Next is the separating funnel, and we have discussed it before. If you need to separate two immiscible liquid, and you need to know how to set it up, as we have mentioned previously in the previous slides. Third is how to set up a burette and take the initial reading. It's very important to know that the burette is a very important analytical technique, whether quantitative or qualitative, as we have previously discussed, but it's very important to know how to read this burette, how to hang it on the stand, how to keep the level of the liquid in a horizontal level to your eye, and how to read at the meniscus, which is the bottom line of the solvent. So whenever you read from the meniscus. Please take care of this. So if this was my reading, my burette reading, how I'm gonna read it? First, you need to know that whenever you read a burette, you always need to take it to the 2 decimal places. So in the balance, we take to 3 decimal places, but in the burette, we take to 2 decimal places. So if this is the 24 and this is the 25, so this is 24.1, 0.1, 0.2, 0.3, 0.4, and this one is 24.5 as it appears here. Then 0.6, 0.7, 0.8, 0.9, and this is the 25. If I want to take the reading of this burette, let's check, then I look at the meniscus, but I have to keep this meniscus at the horizontal level of my eye, not upper and not lower. And then the bottom line of the curve, this is my meniscus, so this will gonna be my reading, which is here 24.75. Why is it here, guys, 24.75? Because let us have a look again on the meniscus. The meniscus was found to be between the 24.7, this is the 24.7, and this is the 24.8. What if my line, this dotted line, is between the 24.7 and the 24.8, then my reading will be 24.75. يبقى in the burette, you will always have one of these options. It's either 0.10, 20, 30, and so on, or 0.15, 0.25, 0.35, and so on. You have no other options rather than these. Either 0.10, 20, 30, and so on, or 1.5 to 5.35, and so on. Please never write any other option rather than these. As we have discussed before, in the separating funnel, we always need to ensure that our tap is closed. So we need always to ensure that our tap is in the horizontal position, unless we need to move down the liquid. But this is not the case in the exam, because in the exam, the burette, you will just need to take the reading. So please don't move the stopcock. Always keep it in closed in the horizontal position. Okay? Whenever you read a burette or you fill it, never to keep it above your head. Always keep the meniscus that you're gonna read in the same eye level if you're gonna read, and even if you fill it, just keep it on your eye level, never higher or lower. Okay, this what happens if you just looked at the meniscus from any other position rather than the horizontal position. The horizontal position will be the only position that will give you the correct reading for the meniscus, but if you looked at it from a higher level, it will give you a false reading, and if you looked at it from a lower level, it will also give you a false reading. So you need always to check it, okay, at the same level of your eye. Please take care that all the readings will gonna be to the second decimal. Don't forget that whenever you take a reading, you have to subtract both the final readings and the initial readings. In the exam, you will be provided with one of them in your sheets, and the other would be practically found in front of you in the burette. So you may find, for example, the initial reading on the stand in your lab would be like this. Can you expect what is this initial reading? Let's check it. This is between the 0 and the 1. So this is 0 0.1, 0.2, 0.3, and this is 0.4, and this is 0.5. However, my reading is in between both of them. So what is it? It's 0.45. This is the initial reading that you will find it practically in the lab. In your exam sheets, you will be provided with a picture having the final reading, as if we did the experiment and we got the final reading. Can you expect now what is the final reading? Please do it on your own. Thank you. Here it's 27.3. And I have to write it 0.30 to the second decimal. Then, how can I know the final titer? I will subtract the final reading minus the initial reading. So it will gonna be 27.30 minus 0.45, giving 26.85. So this would be your final titer. Please, in the exam, you will have to record the three of them in the second decimals, and please don't change anything in the burette that will be provided for you in the lab. Next, can you please try this on your own? I'm having here another example. If this is the initial titer and I'm standing here, what is it? Very good. It's 0.60 to the second decimal. And what is the final titer? 27.00. Perfect. Then how can I get the final titer? Very good. Final reading minus the initial reading, so it will gonna be 26.40. Moving to the third part, which is the interpretation part. Within this part, we need to know more than one info. We need to recall how to read a TLC and how to calculate its RF. We need also to know how to use a flow chart if we are separating two substances having two different miscibilities. One of them is aqueous and one of them is organic. How can we separate them? And how can we extract them? And also, we need to interpret the unexpected yields, whether if it's higher than expected or lower than expected. First, let's start with the TLC interpretation and how to calculate the RF. Why do we use to do TLC, يا شباب? TLC is the thin liquid chromatography. We used to get this silica sheet, fine, and we used to do on it a line like this in the bottom, and this bottom line, we call it the reference line. This would be our reference line. On this reference line, we're gonna place a spot for every reaction we do. So if we did this reaction, for example, 2 times, then I can place 2 spots. If we did it 3 times, then I can do 3 spots. At every spot, I'm gonna place 1 drop from my reaction. And then I will place this TLC sheet. We used to place it in a mobile phase that used to run all over the silica sheet, and that will separate the components of the samples that you added according to the amount of analytes that are found inside. So for example, if here I have 2 analytes, in this pot I have 2 analytes, then after passing your mobile phase, you will get 2 separated spots, A and B. Okay, what you will do in the lab, that you will be given a TLC sheets with different spots, and he will ask you to interpret it. First, you have to interpret that if I'm having here a spot that gave me 2 spots, that means that my sample is having 2 different analytes. But if my sample gave me just 1 spot, then my sample is having inside just 1 analyte. Okay, so this is the difference between the two. Next, you have to interpret, what if, like in example G, I got 2 analytes that are found on the same line. Those means that those 2 analytes are exactly the same. Okay, next you need to know a very important thing. Every spot is having a calculated RF. What is the RF? The RF, we use to measure the total distance between the reference line and the solvent front. A solvent front, this is a line that we used to do it by the pencil to know the maximum height traveled by the mobile phase. So in the exam, you will be given a solvent front and a reference line. The distance between them is, for example, 10 centimeter, then this is the distance traveled by the solvent front. You have to know it. And you calculate the distance traveled by every spot, which is the distance between the reference line and the spot. So let's do this. If you are given this TLC sheet in the paper and you need to calculate the RF for those 3 spots given for the 3 samples, how will you do this? First, I have to say that I will calculate the total distance traveled by the solvent, which is the distance between the reference line and the solvent front. With a ruler, so please don't forget your rulers, you will measure this distance. It will be around 10 centimeter. This is for this case, طبعا. In your sheets, it will be different from one exam to another. And then, you will measure the distance between your sample on the reference line and the distance traveled for your sample. So if approximately it is 1.5 centimeter, then the RF would be the 1.5 over the 10. The distance traveled by your analyte over the total distance traveled by the solvent. Let's do the same for the second sample. I will have the distance traveled by the analyte, which is between the reference line and the analyte, it's 0.3. So I will get 0.3 over the total distance traveled by the solvent, which is 10. And then for this third analyte, I will get the same. The distance traveled by the sample or the analyte, here I will measure this distance, it's 0.7 over the total distance traveled by the solvent, from the solvent reference line to the solvent front, it will be 10. So I will get this 0.7 over the 10. This 7 over the 10, so I will get the RF of 0.7. So this is how we calculate the RF. In the exam, you will be evaluated on two things. First, you will be evaluated on calculating your RF, and second, you will be evaluated on your interpretation. So let's sum up what you will do in your RF. In your RF, number one, you have to measure the distance between the reference line and the solvent front, and this would be the distance traveled by the solvent front, and this will be common for a certain TLC. Next, you will measure the distance between the reference line and your spot. So this would be the distance traveled by your substance, and this will be different for every spot. By taking the distance traveled by the spot over the total distance traveled by the solvent, then you get RF. So we have a different RF for every spot. But what if we have two spots having the same RF? The distance traveled by them over the total distance traveled by the solvent is the same, then this means that those two are the same analyte. So after measuring your RF, you need to interpret. So you will say, if I gave you, for example, TLCF and I asked you to interpret it, what you will say? I will say, here I have two samples, sample A and sample B. In sample A, I got two different analytes, but in sample B, I got just one analyte. So this is the first interpretation. The second interpretation, since I have two analytes having the same RF in A and B, then A and B would have the same analyte in both of them. So this would be your interpretation. What if I did an interpretation for this sheet? Then I have three processes, three samples, A, B, and C. In every sample, I just got one analyte, and the three analytes are different from each other since they have different RFs. Hopefully that I made it clear for you. Now we will check the second part in our interpretation. If we want to use a flow chart in order to explain how can we separate two different compounds by liquid-liquid extraction using the separating funnel that we have previously explained. Let's look. In order to separate two compounds, then now we need to check the nature of those two compounds so that we can separate them within two liquids where one of them would be an aqueous liquid and the other would be an organic liquid. As we have previously explained, the compounds that would dissolve in the aqueous liquid should be hydrophilic or ionizable ones, having ions inside, while the substances that will move to the organic liquid would be hydrophobic or non-ionizable. They are covalently bonded. They have no ions inside. Okay? Then, let's see. If we have those two structures that are appearing in front of you, this is compound A and this is compound B. And we need to separate both of them. First, we need to check the nature of both compounds. This first compound is having here an amine. The amine, with its available lone pairs, make this compound a basic compound. While the next compound, we have a carboxyl and a phenolic OH. The phenolic OH, by the way, ya shabab, it's acidic as well. It's weakly acidic, but it's still acidic, as you took in your theoretical part. But here, the most important functional group, which is the carboxyl, having what? Having the carbonyl with the OH. The carboxyl group donates a proton, turning to be C double bond O and O minus. Since it's acidic, so it donates an H plus, turning to be C double bond O minus. While the basic compound with its amine functional group accepts a proton. It accepts any proton or any positive electrophile added to it. Okay? Then, what will happen if we have those two structures and we need to separate them? What about, first, we will dissolve both of them into ether. The ether constitute what? Constitute the organic layer. So within the organic layer, everything will be soluble because till this stage, both of them are non-ionizable. We have no ions. Therefore, both compounds will first dissolve in the organic layer. So if I have here the separating funnel and I just dissolved my compounds within the organic layer, then I will have here the ether having the two compounds. Then, what if I added HCl? Once I added the HCl here is an acid. What will the acid do? Number one, it will constitute the aqueous layer. Number two, the acid will react with the base. Which one? The one having the amine. So the acid together with the base form what? They form salt plus the water. What do you know about the salt? The salt is an ionizable molecule having a positive cation and having a negative anion. And what does this mean? It means the formation of a salt will allow its movement to the aqueous layer. So now I will get my basic compound in the aqueous layer. However, my other compound will remain unionized within the other organic layer. So here I will have my unionized structure. Okay? Again, let's try to answer this question after all this hints and explanation. You will be given the question like this, and you will be asked, how can you separate those two compounds? Once you look at your question, first you have to decide the nature of the compound. I looked in the first one, I decided that here I have NH2 with an available lone pair, so I said that this is a base. Then I looked in the next structure, I find that it has a carboxyl, so I said that this is an acidic compound. The first step, step number one, he dissolved both compounds into ether. So in the organic phase, I would have both compounds. And then I used a 3 molar HCl. That means that I added an acid. So we say that the acid, it would react with what? It would react with the base. And both of them would form what? They will form the salt that will move into what? That will move into the aqueous layer. So once you separate, you would have an aqueous phase and organic phase. What will be in the aqueous phase? It will be the base that will react with the acid in order to form the salt. So when you draw the structure, you will draw the structure of your base. Very good. But take care. When you draw the structure of your base, you have to convert this basic compartment into a salt because this base functional group reacted with the acid to form the salt. So it's now no more NH2. However, it turned to be NH3Cl. And since here the N is connected to 5 bonds, so it will have a positive charge. It will gonna be NH3 plus and a Cl negative. And this is the salt that will be formed. Okay? Next, here we have the organic phase. We'll get the remaining compound. We had first those two compounds were dissolved in the ether in the organic phase, but once I extracted the base in the form of a salt, then now I will have remaining in the organic phase the other component, which is what? I will just draw it now as it is. Okay, you just need to draw it without any ionization and without anything. You will just need to draw it as it is. Fine. Now let's check if you got the concept correctly. What if you have the same two compounds that we have previously discussed in the previous slide, but now after dissolving both of them in ether, you decided to add 3 molar NaOH instead of the HCl? What would happen? Still, the first compound is the base having the NH2 with its lone pair, and the second compound is the acid having the carboxyl. So once you add both of them in ether, both of them would dissolve. But what if you added a sodium hydroxide? The NaOH is a very strong base, so it will react with the acid. And on reacting with the acid, it will gonna form the salt that would move into the aqueous layer, leaving the other compound unionized in the organic layer. So now my basic compound will be my unionized compound that will remain as it is where in the organic layer. However, in the aqueous layer, you are gonna draw your acidic compound, but you cannot leave it as it is. You need to change this carboxyl group into the salt functional group. How you do that? You just remove the H, so it turns to be O minus, having O minus Na, and this H will form a water with the OH of the sodium hydroxide. So again, once you see this question, but now if you choose to use sodium hydroxide instead of HCl, then what I will do is that I will say that the sodium hydroxide, it will react with the acid, forming the salt moving to the aqueous layer. So I will draw the exact structure, but instead of being OH, I will remove the H. It will be O minus Na. And then in the organic phase, I will get the other compound intact without being ionized, so I'll just draw it as it is. By that, we can separate both of them, one in the aqueous layer and one in the organic layer. Please don't forget that you will be evaluated on drawing both structure correctly, and for the sake of the solid salt structure that will dissolve in the aqueous layer, you will be evaluated on how you ionize it. You either draw O minus and A plus for the acidic functional group, or you drew NH3 plus Cl minus for the sake of the basic functional group. Let's try this example. In this example, you will do a flow chart for both the aniline and naphthalene. You have both aniline and naphthalene, and you need to separate both of them. So first, you will dissolve both of them in diethyl ether. This is normal, since the diethyl ether will be your organic solvent that will constitute your organic layer where the two compounds will dissolve. And then, what shall you add? This will depend on the nature of the two compounds. The first compound is aniline, having an NH2. So this is what? This is a basic compound. While the naphthalene, it has no functional groups. It's neutral. It's neither basic nor acidic. Then, what shall you use to separate them? Can you use a base? Of course, no, because the base will not react with the basic aniline and will not react with the neutral naphthalene, so it will have no use. But I can use a strong acid like the HCl. Why? Because the HCl will react with the base, forming the salt, moving to the aqueous layer, leaving the non-ionized neutral molecule in the organic layer. So again, what will happen once you add the HCl? HCl plus the basic compound, it will give you the aniline salt. So you will gonna draw the same structure for the aniline exactly, but instead of NH2 it will be what? NH3 plus and a Cl minus, as if you added this HCl to the NH2. Then what will be remaining in the organic layer? The other compound, which is what? The unionized hydrophobic naphthalene. And I apologize, my computer drawing. Okay, great. The last concept we need to discuss in the interpretation is explaining the unexpected yield. The unexpected yield, when you do an experiment within the lab, then your theoretical yield should be 100%. This is the theoretical yield that is calculated by the paper and the pen and the calculator. It should be 100%. But once you get into the lab, sometimes your yield can be higher than the 100% or lower than the 100%. So first, you need to know how to calculate the theoretical yield in order to interpret it. If I get example like this, calculate the percentage yield for sodium sulfate when certain grams of the sulfuric acid reacted with excess sodium hydroxide to produce 49 grams of the sodium sulfate. So, in order to calculate the percentage yield, first I have to calculate the theoretical yield, which will give me 100% percentage yield, and then I will calculate the actual yield and compare both of them. So again, the percentage yield is equals to the actual yield over the theoretical yield times 100. This actual yield is the one you measured and you did and you got in the lab. However, the theoretical is the one that was done by the paper. By the paper and the pen and the calculator. If the actual was equal to the theoretical, so you get 100% percentage yield, and this is just a theoretical value. This can never be attained. But what happens in your labs that you either get less than 100, and this is very probable due to more than one reason. You can say in your interpretation, this is maybe due to handling error. This is maybe due to using impure starting materials, or this is due to the presence of your impurities within your product. A lot of reasons that may lead to percentage yield lower than the 100%. Impurities, impure starting materials, handling errors, and many other reasons. However, what if my percentage yield is more than 100%? Of course, this is an experimental error. There is an error in the procedures. How maybe you get some liquid excess in your compound. Maybe it's not that well dried. Maybe, of course, it would be an experimental error that led to the accessing of the 100%. Next, last but not least, we will talk about the numeracy. I know that you had a very nice assignment for the numeracy that in which you had a lot of ideas summarized in, but here we will need to focus about two important calculations. How to calculate the molarity, which is an important method for calculating the concentration, and the percentage yield calculations. First, let's start with the molarity. Let's take this example. Calculate the molarity of a solution containing 30 grams of benzocaine in 250 millis or 0.25 liters solution. First, you need to know that there are two important rules. First, the number of moles rule, and next is the molarity rule. Whenever you get the molarity question, you need to recall those two rules. And you need to recall them because the SChemEs lab is not an open book exam. So please recall them carefully. The number of moles is equals to the mass over the molecular weight, or the mass over the molar mass. So if I here have the mass 30 grams over the molar mass, then I get the number of moles. The molarity, the number of moles dissolved in the volume, but this volume must be in what? In liters. So even if he gave you 250 milli solution, you need to convert this into liter and to use the 0.25. So in order to get the molarity, I will get the number of moles calculated over the volume in liters. So I will write it 0.73. You either write the unit mole per liter or you just write a big M for molar. Please, for the molarity question, you need to know three things by heart. Number of moles, rule, mass over the molar mass, molarity, number of moles على volume in liters, and please take care of the units. Let's try this. Please try it on your own before I answer it with you. You can pause the video, try it, and then play it back. How many grams of acetone, and he's giving the formula C3H6O, required to prepare 1.5 liters of 0.5 molar solution? Still, since you have the molarity, first you have to know that I will use two rules. The first rule is the number of moles is equals to the mass over the molar mass, and the other one, that molarity is the number of moles over the volume in liter. We can find that whenever we have a compound, then first we need to calculate its molar mass. So here, the molar mass would be 3 times 12 plus 6 times 1 for the hydrogen plus 1 times 16 for the oxygen. You calculate them and then you get 58 grams per mole. Take care whenever you will calculate the molecular weight of any compounds. Kindly elaborate your answer in a stepwise manner as it's shown here in order to guarantee your marks. Because if you just made a mistake in the carbon, I will not deduct for you the whole mark. But if you just wrote for me the final answer and you had a minute mistake, then you will lose the whole marks. That's why it's highly preferable to write the molecular weight calculation in a stepwise manner like this in order to reduce the deduction of your marks. And please don't forget the units to be gram per mole. Now I got the molar mass or the molecular weight, then now I can substitute in the two equations that we all know. The first rule is molarity equal number of moles over the volume, and this volume have to be in liter. Here I'm supplied with the molarity and I'm supplied with the volume. So in order to calculate the number of moles, what do? I just simply multiply the molarity by the volume in order to get the number of moles. So it's 0.5 times 1.5 liters, then it's 0.75 moles. Next, we write the second rule. The number of moles is equals to mass over molar mass. Here the same. I have the number of moles and I calculated the molar mass, 58 gram per mole. So I'll just multiply the 58 multiplied by the 0.75. Then I can get the mass to be 43.5 grams. Please don't forget the units. At last, we will gonna discuss the percentage yield within the numeracy testing. So, regarding a percentage yield, as we have discussed before, we should have two yields. The theoretical yield that is calculated on the paper, and this is the maximum amount that you can get, but this is just a theoretical number. But actually, what you get is maybe more or less than this number. So, in order to evaluate this, we need to calculate the percentage yield, which indicates the correlation of the actual yield to the theoretical yield. It indicates the amount that is actually obtained relative to the amount that theoretically should have been obtained. So we get, for the percentage yield, we get the actual over the theoretical times 100. The actual, the one you did in the lab, the theoretical, the one you calculated on the paper. This percentage yield might be more than 100 or less than 100, and you shall know how to interpret this as previously mentioned. Let's have an example and let's discuss it together. Like in molarity, we said that you have two main rules that you need to know: how to get the number of moles, mass over the molar mass, and how to get the molarity, number of moles per volume in liter. Here also in the percentage yield, you will have some steps. It's a certain sequence that you will need to follow to calculate the percentage yield, and we discussed this before within your calculations lecture. First, when I ask you to calculate the percentage yield for 100 grams, for example, carbon dioxide that are produced from 1 mole of butane, then first I have to write the equation. It's full equation and balanced equation. So the first step, you need to make sure that all the equation is balanced. Step number 2, you will check what will be your limiting reactant and what will be your product. We will not get you into the hassle of knowing the limiting reactant into the exam, because the one that will be the major one, okay, if he didn't tell you in excess, anything found in excess cannot be the limiting reactant. Any gas cannot be the limiting reactant. Then here, he's telling you 1 mole of butane, then the butane is my limiting reactant, and it will gonna produce carbon dioxide, so the carbon dioxide is the desired compound to be synthesized or to be analyzed. So this is the one for which I'm gonna calculate the percentage yield. Then, the next step, we will see the number of moles of the carbon dioxide that will be produced if we have a 100% yield. In other words, what is the theoretical yield of carbon dioxide but in moles? What if we have a total consumption for the given amount of butane? To know this, we first have to consider the ratio. It means that in this chemical equation, for every 2 moles, we get 8 moles of carbon dioxide. But in our case, do we have 2 moles? No, we have 1 mole. Then how many moles of butane will be produced then? So again, I say, for this chemical equation, due to the stoichiometry of this equation and after the balancing, we got that for every 2 moles of butane, we get 8 moles of carbon dioxide. But in our case, we don't have 2 moles of butane, we just have 1 mole of butane. Then, how many moles of carbon dioxide will be produced? I will do a cross multiplication. So it's 1 times 8 over the 2. Then, for every 1 mole of butane, I get 4 moles of carbon dioxide. So this would be the theoretical yield of carbon dioxide, but in terms of moles. Since we need it in terms of grams, so we need to convert those number of moles into grams. How do we do this? We use the previous rule. The number of moles is equals to mass over molar mass. Then the mass would be equal number of moles multiplied by the molar mass. Exactly similar to the previous rule. Here I have the number of moles is equals to 4, and I will need to know the molar mass of the carbon dioxide. So it's 12 times 1 and then plus 16 times 2. So it will be 44 gram per mole carbon dioxide. 4 multiplied by 44 will gonna be 176 grams carbon dioxide. So this is the theoretical yield that will be produced theoretically. But in the lab, we didn't get 176. However, we just got 100 grams. Then, to calculate the percentage yield, we will get the actual produced 100 grams over the 176 theoretical grams times 100, so the theoretical percent will be 56.82. If he asked for interpretation, then you will say that this theoretical yield is much lower than 100. This experiment is not that efficient. Maybe we need to change the process, or we need to change the conditions. Maybe we need to heat more, we need to use catalyst, maybe we need to check for the impurities, maybe we need to do better handling. You can write whatever you want as an interpretation in order to interpret this low yield. Let's have another example. Calculate the percentage yield for sodium sulfate, and this is the one that we have just mentioned before, but here we will do it in steps. When 32.18 grams of sulfuric acid that will react with the sodium hydroxide to produce 37.91 of sodium sulfate. So before starting, you will analyze that. If this is the equation, number 1, I need to check, is it balanced? Take a moment, please, to check. Yes, it's balanced. At this side, I have 4 H's, I have 2 NA's, and I have 5 O's and 1 S. On the other side, also, I have 4 H's, 5 O's, 2 NA's, and 1 S. So it's balanced. Then I can use this equation. Then I will need to check what will be the limiting reactant. Here, he told you that you reacted sulfuric acid with excess sodium hydroxide. So sodium hydroxide can never be my limiting reactant or the one that will control my reaction. But, however, I will use the sulfuric acid in order to check for the theoretical yield that will be produced for the desired sodium sulfate. So the correlation would be between the sulfuric acid and the sodium sulfate. From the stoichiometry of this balanced equation, what's the correlation between them? It is 1 to 1. So next, in order to calculate the number of moles that will be produced, I have to consider the ratio. So since I have 1 mole of conc sulfuric, that will give me 1 mole of sodium sulfate. Then, in my experiment, did I use 1 mole of conc sulfuric? Actually, no. But I used 32.18 grams. So the question is, those 32.18 grams constitutes how many moles? So I use the same rule. The number of moles is equals to the mass over the molar mass. The number of moles of the H2SO4 used is equals to the mass, 32.18, over the molar mass, which would be 98.08. How do I get it? The atomic weight of hydrogen multiplied by 2 plus the sulfur plus 4 times 16 for the oxygen, so I get 98.08. By doing this division, 32.18 over the 98.08, then I can get the number of moles of the H2SO4, which would be 0.328 multiplied by 1 over 1, so 0.328 moles of H2SO4 would give me 0.328 moles of sodium sulfate. Now I get the number of moles, but in order to get the yield, then I will need to convert the number of moles into yield. How? The rule says number of moles equals mass over the molar mass. So the mass would be equal to number of moles multiplied by the molar mass. But don't forget, the number of moles is 0.328 and the molar mass now is the molar mass of the sodium sulfate, the one for which you want to calculate the yield. So you need to calculate it. 2 times the atomic mass of the sodium plus the sulfur plus 4 times 16 for the oxygen, which will give you 142.04 gram per mole. So now I will do the number of moles calculated 0.328 multiplied by 142.04. I will get 46.59 grams, and this would be my theoretical yield. Finally, to calculate the percentage yield, you will look for the actual yield that was produced in the lab, which is equal to 37.91 over the theoretical, which is 46.59 grams, and you will calculate it and check its percentage whether it would be lower or greater than the 100. Coming to another assessment that will gonna take place within your SChemEs exam is the SChemSketch. The SChemSketch is a program in which you can draw your chemical structure as well as many other tools that will help you to visualize the chemical structures you have and the chemical reactions on the pieces. It's like when you want to write a paragraph, so you go to the Word. If you want to draw a table, you go for the Excel. If you want to do a presentation, you go for the PowerPoint. So if you want to draw a chemical structure or any related chemical reaction, then you will need SChemSketch. There are a lot of other programs and softwares, but SChemSketch is a very easy one, and also it is freely downloaded. Let's explore more, and you have a detailed workshop with how to draw on your SChemSketch. But most importantly, you need to remember that in order to draw your structure, you need to get here structure or draw. Then you have several atoms on the side from which you choose if you want to draw a carbon, hydrogen, nitrogen, oxygen, etc. You have here the bonds, so we choose the first one, which is a single bond to draw, and then here we have some templates that are already made. For example, if you need to draw a benzene, you can just pick the benzene directly. If you need a carboxyl, you can just go to the carboxyl directly, and so on. And then also, this is a very important step, that after you draw your structure, you need to clean it up. So, for example, if I drew something like this, if I drew a benzene molecule like this, okay, then it's ready-made. And then I went and I choose this pen and I drew a single bond like this in order to do MSI. But actually, this geometry is not correct. So I will go and pick select, which is this button, and then I'm gonna select my structure, and then I'll go and click on clean up your structure, and by that I would get the correct geometry. This button enables you to generate IUPAC name from your structure, but don't forget that before doing any step, you need to select. So remember that this select button is very important. You first need to select anything before you can do any action. Here, this is a very important button, which is calculated properties. The calculated properties might calculate for you the molecular weight, the molecular formula, the melting point, refractive index, and a lot more. They are theoretical calculations that are recorded for your molecule or your structure. So also, you need first to pick your
you need to select first your structure, okay, and then you go and click on this calculated properties, so you get a window with all the details needed where you might find your molecular formula and molecular weight. So this is very important. Also, there are some ready-made templates. So if I asked you to draw for me a sucrose, for example, instead of drawing the sucrose, which is a very big structure relatively, you can just go into the templates and you will find it ready-made. And there are a lot of templates that are already there. I encourage you to go and check them. This button shows you the 3D structure of your molecule. Here, also after selecting your structure, you can click on the advanced search in the databases, and it gives you all the details about your compound, whether in ChemSpider, eMolecules, or PubChem. So this is very important if you need to know more and more reported details about your structure. Here, this is the toolbar. You can see the most important thing is this rubber by which you can erase anything you have done, but don't forget also, if you want to use it, you need first to select your structure or to select the bond or to select the atom, whatever you want to erase, and then you choose this rubber to erase it. If you did something wrong and you need to go back, you can just click on this button. And also we have a very nice tools here, which are those ones up there that shows you can add a plus for your chemical reaction or an arrow. Also, the arrow of the chemical reaction might have some conditions over it. So those are some beneficial tools that you can use while drawing your chemical equations.
Last but not least, in order to prepare well for your schemes, please review well this presentation, as well as any skills that you have used in your laboratory sessions before, but you need to focus on the skills in this presentation in specific. Watch the videos that were provided in Lab 1. They will help you a lot while handling the separating funnel, the vacuum filtration, how you use it, how to separate, how to shake, how to vent, how to keep the separating funnel standing, and the other glassware manipulation. So you will have demos and videos in the Lab 1 that will help you a lot in this. Please be there on time. Kindly make sure that you have your calculator, pen or pencil, the lab coat, and a ruler together with you. No mobile phones will be allowed. If you were not present on the time of the lab, you will not be allowed to enter the final exam. So kindly be there on time. And regarding the Ramadan slots, كل سنة وانتم طيبين, the morning session starts at 9 and the midday session would start at 12:15. So just kindly make sure to be there on time. Wishing you best of luck, and feel free to visit any of your tutors to ask them for any help before your labs. Have a good day.